Hello and welcome to another LeetCode video. Today we're going to be doing the final dream problem of the day for June 30th, last day when you can still cross. And we're actually going to go over the solution that I found that I did not come up with myself. I will briefly talk about the one that I came up with myself, but I think the one that I found in red is more interesting, so we're going to talk about that. So in this problem, you are given a grid, and the grid has all lands, and then you have this cells. And so the cells just tells you at every day, one of the lands turns into a water. So as you can see from this example one, we start with all lands, and lands are represented as zeros. And then at every day, one of the lands turns into a water. So it starts here, and then in one day, cell 1-1 turns into a water. And so these cells are also one indexed. So 1-1 is actually over here. So this 1-1 turns into a water. And then the 2-1 turns into a water, which is here. And then the 1-2 turns into a water. And finally, the 2-2 turns into water. And so what you're being asked in this question is, return the last day where it's possible to walk from the top to the bottom only by walking on land cells. So pretty much that means that you can go from any cell on the top to any cell on the bottom. So we could see that it shows in the picture. In the first part, we can go straight down. In the second part, we can go straight down. Then we can go straight down, but once there's 3 water cells, we can't. Okay, and so in the second picture, they show us the same kind of thing. And so you can see that once the whole top row is filled with water, we can't go straight down because there's no top cell we can go down. So now we have the third picture. You can go down day 1. You can go down day 2 this way or this way. You can go down the next day. You can still go down. So any path is valid from any cell on the top to any cell on the bottom. And now finally we can't go down on this last day. So this would be day 3. Yeah. Okay. And so we need to figure out how we can do this. Yeah, right. So it'd be day 3 because this is day 0, day 1, day 2, day 3. Okay. And so we need to figure out how we can do this. So there is one way to do it that's pretty straightforward, and I'm just going to talk about that really quickly first, and then we're going to go into the more interesting way. So the really easy way to do it, well, not so easy, but easy enough, is you can just take every single state. And so you actually don't want every single state. So first of all, you can realize that for these cells, like let's say these cells, let's just say we have these entries in the cells, like entry 0, 1, 2, 3, 4, 5, 6, and so on. So after a certain point, you're not going to be able to go down. So let's say that point is this. After some point, you're not going to be able to cross. So all of these will be no solution, right? You can't cross. And all of these will be you can cross. And so what you can actually do is you can actually just binary search into this. Just pick a random day. And so when you pick a random day, you can actually create the grid at that day, right? So you can just figure out what would be the grid at that day with these cells. You can update the cells up to that day that you picked for the grid. And then you can do a breadth first search from that day and see is there a solution that's viable? So let me show you how that would look. Let's say we take this last day here, right? We just randomly binary search this last day. So we would have something like this. Yeah. And then we'd have these land cells and these water cells. So pretty much all you're going to do is you're going to take every single land cell that's on the top row, put those into a queue, and then you're going to breadth first search and see if you can get to the bottom from any one of those. And if you can't, and so that's just the standard BFS, right? You just put all these cells into a queue, and then if you can get to the bottom from any of those with a standard BFS, then you can say that that day works as a solution. And so if that day does work, let's say we pick this random day, like this day here. So let's say so let's say we don't know the solution. We just pick a random day like 4. And then if this does work, so let's just say it does, like D. If it does work, now we can binary search again on this left side, and we can keep doing that until we get the smallest possible day that or actually I think they asked the last possible day, right? So it'd be the other way. So if the day does work, you would want to go over here and then you'd want to try these days and see, is there a day greater than here? And then you would just record like the last day in your binary search that you were able to cross. So it's a pretty straightforward problem. So you just do a binary search in this, and then whatever days you pick, you do a breadth first search in the grid with the states from cells. And so the way that would work, so the time and space complexity would be, so you have a binary search on this bottom, which would be the length of cells, right? So that's going to be like log the length of cells, which is row times column. So it would be like log row times column. And then you have to search, you have to do a breadth first search every time, so it would be like row times column times row times log row times column. So binary search with a breadth first search. And I think that's like a pretty straightforward problem to do. Like you should be able to do that solution, but we're actually going to go into the more interesting solution here. And I think it's quite clever. And so I wanted to go over that one. And so this solution is going to rely on the fact that we're going to be using union find for disjoint sets. So hopefully if you heard of union find for disjoint sets, pretty much what that does is just like a basic understanding is it connects nodes together. And then we can find if two things are connected. And the way we're actually going to do it is we're going to base it off of land. So if we have these cells, right, if we have these cells, what we can do is we can actually start with a grid that's completely full of water. And then we can traverse backwards in cells. So let's say the cells has a bunch of elements like 1, 2, 3, 4, 5, 6, 7, and so on. We can traverse this way. And for every single cell that we need to change, we're just going to change one. We're just going to change one land into water. So let's say we're here. And this is saying like, you know, on the last day, this cell turned into a water. So then we would be going backwards and would say, okay, now that we're here, let's turn that back into a land. And then for the cell that we visit, we're going to try to connect it to every other land node that's near it, right? So we're going to try to connect it with every other land node that's near it. So let's just say we go backwards from actually, let's take this example here and let's go backwards. So let's do that. Let's actually, so the last cell would be 3, 1. And so remember, these are 1 indexed. So we'd go to 3, 1 and we'd say, okay, where's 3, 1? So it's row 3, column 1. It's going to be the cell right here. We're going to turn that into a 0, and we're going to connect it to every land that is near it. So right now there are no lands that are near it. Then we're going to go to 3, 2, which is this land, and we are going to connect it to every land that's near it. So there's going to be a connection right there. And now we have, so we did 3, 1, we did 3, 2, right? We're doing these cells over here. Now we have 2, 3. And so that's going to be row 2, column 3, which is right here. There is no land near it. Now we have 1, 3. And I'll kind of show you like what the end state you need to have is. So 1, 3 is row 1, column 3, which is here. And then since we turned this into a 0, we're going to connect it to every land that's near it. So we're going to make a connection here. Okay, now we have 1, 1, which is going to be this cell here. So we're going to connect it to every land. Okay, so now is when we actually have a viable solution. And the way we know we have a viable solution is we're going to have a node with all the nodes in here. And if we can reach, if this node is connected to this top node, so if any one of these nodes on the bottom is connected to any one of the nodes on the top, I'm going to show you how to do this, then we return true. And so I definitely think it's a really clever solution because we are taking multiple cells and actually making them a node, and I'll show you how to do that. And this is, if you think about the time complexity here, so what we're doing here is we're traversing cells backwards every time we are just searching for one number, and we are updating all the elements near that, which is, you know, constant time. And so this solution would actually be R by C, so it's faster than the breadth first search with a binary search. And I think it's definitely trickier to come up with. And like even if you know union find, now that I told you all this, it would still be hard to code. And I think that's like a sign of a good problem. Even if you know the solution, it's still not easy to code. Like, I would definitely encourage you to figure out how you would code it, knowing that that's how you would do the solution. Traverse backwards and find and make these connections. And once there's a connection between the top and the bottom, you would return the day that happens. And so if you think about it, there is some index in these cells, right? Where like there's some index that's the last day. And so when we traverse backwards, when we go this way, the first day that there's a connection is the last day that was possible to cross. So as soon as we hit a connection by going backwards and using land, that's going to be the last day that it was possible to cross. Okay, so now we have a couple other things to take care of before we can actually solve this still. And so let's go into that. So let's actually make some more space here. Okay, so for a union find, the union find is typically given a number of nodes, right? And so let's say we have this grid. And we have these nodes and their whatever values, doesn't really matter. We need to figure out how many nodes we actually give our union find. And so what we're actually going to do is we're going to have, so the number of nodes, we want our nodes to be numbered like this. And this is how I'm going to do it anyway. So our nodes are going to be numbered like this in our union find. So we're going to give it a number, and then we're going to have one more node for the top. So this big node is going to be node number 9, and this big node is going to be node number 10. And then we are searching for a connection here between node number 9 and node number 10. So when we call union find, we're actually going to give it, you know, like how many nodes we're going to give it. We're going to give it row times column plus 2 nodes because we want this top and this bottom. And so the way union find works is you give it nodes and it will connect them for you, and it can also check if they are connected. And I'll paste the code. You know, I'll show you the code for union find, and I'll paste where it is in LeetCode if you want to look at it. And I can also actually paste my code in the description if you want it. But so that's pretty much what the union find actually does, is it makes connections between nodes. And so that's what we need to do. And then every time we visit a cell, so like I said, every time we visit a cell and we change it to a 0, we do need to connect it with all the land near it, but we also need to check. So let's say we visit this cell. If the cell is in the bottom row, then we also need to connect that cell to the bottom row. And then if the cell's in the top row, we need to connect that cell to the top row. And then finally, after we make all these connections, we just check, is our top row equal to the bottom row? So if top equals bottom, if they're connected, right? Not equals, but if they're connected, then we are able to actually return that we are able to cross. Okay? And so we need that, and then we need one more thing here. So now that I showed you how we're going to number these nodes, it's going to be important to figure out how we actually get a number from a row. Like, so these are indexed like this, right? So we need to figure out, how do we actually get a number? Like, how do we get the 7 if we're actually here? And so the way that's going to be, like, let's focus on the 7. The way to get this number is actually going to be the row we are at times the total columns. Let's just call that like big, or like big call or something. That's what we're going to use. And so if you think about it, that just means like how many total columns we've passed. So let's say the columns here is 3, then the row we're at is 2. That means we've passed 6 total items, and we have. So we've passed 6 total items. That's why we're on this row. But there's a little bit more here. We also need to add the current column we're on. So we need to do this, like the row we're at times the total columns plus small column. And so now if you think about that, let's figure out what that would look like for this example. So the row we're at is row 2. The number of total columns is 3. And the column we're on is column 1. And so we'd get a 7. So that's how we would actually get this, like, what's the actual n integer number that we're going to use to index into our union find to connect these. Okay, and I think that's everything we need. Yeah, and then like I said, our top will be, you know, in this example, our top will be 9, and then our bottom will be 10. So we're going to need to pass it. How many elements do we need to pass into union find? We're going to need to pass in rows times columns plus 2 elements, but they're going to be 0 indexed. So they're going to be like this 0, 1, 2, and so on. And yeah, like for example, for this 0, 0, if you did this problem right here, it would be row 0 times columns, which would be 2, plus the column we're at, which is 0. And so that's 0. So that's how you get a number out of an index you're at. And yeah, I think that's it for this problem. So let's actually dive into the code and let's go into how it would work. Okay. So this is just a standard union find. I didn't write it myself this time. I just copied it from LeetCode. Sometimes I write it myself. It depends, like, you know, what I'm feeling. I can write it myself. I would definitely encourage you to, if you had to be able to write this yourself in an interview. But, you know, make sure you know how it works. And yeah, so I'll briefly describe it. So you have you have roots for every node, and you have a rank that symbolizes the size of like the tree, like how many elements are in the actual how many elements are actually in like the path with this node. And then find finds the parent of the disjoint set, and union makes the link between two nodes. And then connected just checks if they are connected or not. Okay, so let's actually go over the code. So this first part's pretty straightforward. We just have the directions like we normally have in a BFS DFS, because we do need to still check all of these cells near the cell we're at. And we're going to make an initial grid with just a bunch of ones. So it's just going to take, like for this example, one, it would be 4 ones. For this example, they would all be ones. We're starting at the end and we're working backwards. Then we make a union find with the number of rows and columns, like I said, +2 for the top and the bottom. And then the numbers we're going to use for union find. So like, let's say this rows and columns is 3, right? Like I showed in the other thing, the top would be, 10. I think I used, let's see here. For the top, I used UF elements -1. So the top would be 10 here. Sorry, it would be 9. And then the bottom would be 10. So I did add this little elements thing just for myself. This wasn't originally in the code. So I just said, like, this is how many elements are in the union find. And so in here, the elements would be, this would give you 8. Let me just, no, actually, no, it wouldn't give you 8. Because we're going to pass in 11 elements, right? This would be 10. Yeah, that would be 10. Okay. So anyway, so then you would have like 9 and 10 for your top and your bottom. So now we are going backwards through the cells. And then because these cells are 1 index, we have to actually subtract 1 from each of these cells. So like this 2, 3 is actually index 1 and column 2, not 2, 3. So make sure you subtract 1. Now, this is that number calculation that I said, where we have some row and some column. Now, how do we actually get the number for our union find, which is this? Like we have some index. How do we actually get the number that we need to use to represent that node in the union find? So we're going to have nodes in the union find 0 to 10 if it was a 3 by 3 and so on. Okay, now we need to change the water into the land going backwards. So whatever cell we're at, change it into a land. Now, check all its neighbors. If they are in not an out of bounds location, we can combine them. And the nice thing is, if you do a union with a cell that, like if you do a union with cells that have been connected already, it doesn't do anything, which is kind of nice. So it's okay like repeating your work. Like it'll just, as you can see in this union, if the roots are different, it'll do stuff. But if the roots are the same, it just won't do anything. So it's totally fine to do in another union. You don't have to check like if they're connected or whatever. So then you connect, like you change one cell into a 1, or sorry, change one cell into a 0. Then you connect it to every other cell that you can next to it. And now this is finally our conditions. So if the thing we just turned into a land is on the top, we need to add it to the top. So we would do a union with the top. If it's on the bottom, we need to add it to the bottom, and this is our return condition. I don't think we actually need this return -1. There should always be a valid output. So I think if we run it without this, that should still work, because at some point there has to be a valid output. Yeah, and so you can see it's a pretty efficient algorithm this way. It's more efficient than the BFS and the binary search, like I said. And so this is our return condition. If the top and the bottom are connected, meaning any node from the top is connected to any node from the bottom. And I think this is like the clever part about this is I never really did something where I had like a set of nodes represented by one node. Essentially what they're doing, like they're saying any node here is one node is the top, and any node here is the bottom. I've never like thought of things that way. So I do think that's like good to know, and maybe you can do that. You can use that for other problems. Okay, so now let's think of the time and space complexity here. So for the time, like I said, what we're doing is we're initializing a grid to all ones, and we're going backwards. And then we are just changing one cell at a time to a land. We're connecting it to every possible land near it. And then what we are doing is we are checking if the top and the bottom are connected. So in an ideal union find, it's not exactly like this, but all these algorithms are technically big O of 1, I think. They're not exactly like that, but that's the argument. Is like this find, this union, and this connected is big O of 1. So assuming that's the case, then we have a time of number of rows times number of columns, because for each index, all we're doing is changing one value to 1, checking 4 directions, and just checking if something's connected. So that's just all constant time stuff. Okay, and then for the space, So obviously we make a grid. We make a new grid. We can yeah, I don't think we're given a grid, but we can like we have to use this grid. So that's already rows times columns. But also in the union find itself, when you give it some elements, you're going to make a root array and a rank array. And so those are also big O of n, where n is rows times columns. So those are going to be rows times columns. And let's see. So we have the grid, top and bottom, and all that stuff is just nothing. Yeah. So like I said, in this union find, this is big O of rows times columns, this part here. And then this is also, this grid is also O of big O times rows times columns. And that's actually going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I definitely encourage you to code this one up yourself. Even if you know the union find, like I said, just because you know the solution, this one's hard enough to where you can, like, I literally told you the solution and you can try to code it and it's still not that easy, I think. So it's definitely one that's good practice. Okay, so I will see you in the next video. Thanks for watching.